Cancer is the second leading cause of death globally. About 1 in 6 deaths is due to cancer. For example, can you believe that in 2018, cancer was responsible for around 9.6 million deaths worldwide? However, it is true that since 1990, a downtrend in cancer death rate has been detected. Thanks to research and scientific advances, the early detection of cancer is nowadays possible. But it is not enough. The most commonly used treatments for fighting cancer, such as radiotherapy and chemotherapy, remain the same since the beginning of last century and are not effective enough. Additionally, these treatments affect both indistinctively to the cancer and to the healthy cells, leading a large list of side effects, such as nausea, fatigue, hair loss, pain, and so on. Besides, more aggressive cancers require higher doses, making these treatments even more dangerous than the cancer itself.
And therefore emerges THERACAT, a Marie Curie European training network which aims to develop a targeted cancer therapy more effective and exempt of side effects via a two-step strategy by combining nanotechnology and bio-orthogonal organometallic catalysis. Does it sound challenging? It is. For this reason, 13 PhD early-stage researchers from 6 different academic institutions, as well as industrial partners active in the pharmaceutical field, join forces and their extensive experience in medicine, chemistry, and microscopy.
Let's talk about our strategy. Our aim is to make anti-cancer drugs specifically at the tumor sites in the body using a bio-orthogonal approach. Let me make you familiar with the term bio-orthogonality. It's a combination of the word bio, which relates to something happening inside our body, and the word orthogonality, which means two molecules react together, leaving the environment around it intact and healthy. In our case, we make use of a bio-orthogonal organometallic reaction, in short BOOM reaction, where a metal is used as a catalyst to activate prodrugs inside the body. A catalyst is an agent that can speed up a chemical reaction, and if it's also bio-orthogonal, it's called a bio-orthogonal catalyst. So in short, in our case, we make use of a bio-orthogonal catalyst to activate prodrugs into toxic anticancer drugs at the tumor site.
So in THERACAT, we propose a localized cancer therapy in 2 steps. At first, we will deliver nanoparticles embedded with catalysts to the tumor site. Next, we will deliver prodrugs which are not toxic to cells using the same approach. The proper design of these nanoparticles ensures exclusive delivery to the cancer cells, avoiding their performance in healthy tissues. At the tumor site, the prodrugs are converted into active anticancer drugs by the catalysts, generating a strong localized effect that eventually kills the cancer cells. So we aim to develop different types of nanoparticles carrying catalysts and a range of prodrugs to improve the current cancer therapy.
Nanotechnology is very promising. In recent years, research on nanoparticles has skyrocketed, with thousands of articles being published. However, there are currently less than 60 nanomedicines approved by the FDA. Basically, less than 1% of nanomedicines that enter clinical trials are successful. Why? Because at the nanoscale, things are difficult to characterize, so we can poorly predict their performance in the complex human body, until today.
So, we account in our team of experts who use the most powerful and state-of-the-art imaging techniques like super-resolution microscopy, which has a 10-fold higher resolution comparing to the conventional optical microscopy. This nanoscopy will allow us to understand and visualize the interaction of our nanomaterials with the cellular components and the single particle and the single molecule level.
Besides, thanks to our experience in 3D cultures and microfluidic systems, we can better mimic the conditions inside the human body, and thus we can pre-select, compare, and predict the performance of different nanocatalysts and prodrugs before going to in vivo models, thus increasing the chances to succeed in clinical trials.
One of the final steps of our project will be to see whether the catalyst or the product are specifically located at the tumor site. To do that, we will use PET imaging technique in our animal studies. PET imaging allows us to use radioactive substances that emit radioactivity, a type of radiation that can be easily detected by scanners like the one you see behind me. Using the technique, we can easily attach a radioactive substance to our catalyst or our prodrug, inject it to a patient, and then scan it in a PET scanner. The final result will be an image which will reveal to us where the catalyst is located.
So, in THERACAT, we are using smart chemistry and the state-of-the-art techniques to develop a two-step localized cancer therapy. We do believe we are one step closer to cure cancer. Thanks for watching.